Good morning, everyone. Welcome to the second lecture on Introduction to Stability. In the last lecture, we have seen the examples of stability failures such as Rodon Point collapse, Hyatt Regency Skyway collapse, I-35 bridge collapse, El Ambience Plaza collapse, Tay Bridge collapse, Tacoma Narrows Bridge collapse. One thing that can be observed is that all the failures were catastrophic and sudden in nature. So this is the reason that we study the concepts of stability, because the examples of catastrophic and sudden failures discussed before clearly indicate that it is imperative to study the concept of stability. So before we go further, we need to understand what are the factors one should consider to design a structure. We call it the 3S. The first is the strength, the second is the stiffness, the third is the stability. The strength and stiffness, basically we have a fairly good understanding of the two S. The third S is the stability, which is what we will be discussing in this class. So the first S, strength, refers to the maximum stress that a material can resist before deformation or fracture. For example, yield strength as well as ultimate strength. What you see on the right side is a stress strain plot of a mild steel. We also call it as tensile test or coupon test. The point A represents the proportional limit, the point B represents the elastic limit, both of which are within the elastic limit, and the point C represents the yield strength, point D represents the ultimate strength, and point E represents the fracture or breaking point. So the left side of the curve to point D is called the elastic region, and to the right side of the curve, which is slightly lesser gray in color, is called the plastic region. The next one that we're going to talk about is the stiffness. Stiffness is the rigidity or the resistance offered to deflection. There are several different types of stiffnesses, starting with axial stiffness, bending stiffness, as well as torsional stiffness. So what is stability? We will discuss it further in this course. That is the third S. So these concepts that we have discussed is also available in the IS 800, which is called limit states of design in the codal provisions. One is called the limit state of collapse. The other one is called the limit state of serviceability. The limit states of collapse deals with the strength and stability of the structure under maximum design load. The limit states of serviceability deals with deflection, cracking under service load. It also includes durability, fire resistance, vibrations, corrosion, etc. This is exactly what is given in the codal provisions. Section 5.5 of IS 800 gives the factors governing the ultimate strength. For stability, it is 5.5.1. The next one is the limit state of serviceability, where what we have discussed in the previous slide is basically given here. So the stability-based design equations are also present in our IS 800. Section 7 represents the design of compression members. Section 8 represents the design of members subjected to bending. And Section 8.6 represents the design of beams and plate girders with solid webs. All these equations are derived based on the concepts of stability. Now, let's look at the deeper understanding of the stability. We will go back to the definition of stability and we'll continue our conversation in the next few slides. Concepts of stability. What is stability? The definition indicates that a sudden change in geometry of a structure or structural component under compression resulting in loss of ability to resist loading is defined as instability. Instability can lead to catastrophic failure and it must be accounted in design. So why did we define instability instead of stability? Because stability is not so easy to define. Every structure is in equilibrium, whether it is in static or dynamic condition. If it is not in equilibrium, the body will be in motion or a mechanism will happen. A mechanism cannot resist loads and is of no use to a civil engineer. So stability qualifies the state of equilibrium of a structure, whether it is in stable or unstable equilibrium. States of equilibrium. There are three states of equilibrium. The first one is called the stable equilibrium. A structure is in stable equilibrium when small perturbations do not cause large movements like a mechanism. Structure vibrates about its equilibrium position. The second state of equilibrium is called the neutral equilibrium. The structure is in neutral equilibrium when we can't decide whether it is in stable or unstable equilibrium. Small perturbation cause large movements, but the structure can be brought back to its original equilibrium position with no work. The third one is also known as the unstable equilibrium. A structure is in unstable equilibrium when small perturbations cause large movements and the structure never returns to its original equilibrium position. Whether an equilibrium state is stable, neutral, or unstable can be determined using the perturbation technique. So, what is perturbation technique? Perturbation is nothing but a small deformation that you apply and remove the force, and once the structure returns to this original configuration, it is stable. If it does not return to the original configuration, it becomes unstable, or if it moves away and it stays at a certain point, then it's called neutral equilibrium. So let's look at stable. So if the body returns to the equilibrium position, as you can see from the right side, there is a concave surface. You put a small a ball or a roller object, and then you apply a small perturbation to the stable object here, and then it moves to the right or to the left depending upon the direction of the perturbation, and it returns back to its original position, and this is called the structure is in stable equilibrium. Unstable is if the body continues to move further away from the original equilibrium position. It can be observed by keeping a convex surface where a small ball is placed on the top, and if you apply a load, it moves away from its original equilibrium position and never returns to the original position, which is called unstable equilibrium. The third one is the neutral equilibrium. If the body remains at an adjacent position, neither returns to its original position nor continues to move farther away from its equilibrium position. Thus, stability talks about the equilibrium state of the structure. The definition of stability has nothing to do with the change in geometry of the structure under compression. So, the change in geometry of a structure under compression that results in its ability to resist loads is called buckling. As you can see from the picture, as long as the compressive load P on a member is relatively small, increases in load result only in axial shortening of the member, which is stage 1. However, once a certain critical load P critical is reached, also in stage 1, the member suddenly bows out sideways, which is stage 2. This bending leads to large deformations, which in turn cause the member to collapse. The load at which buckling occurs is thus a design criteria for compression members. The structure buckles from state 1 to state 2, where state 2 is orthogonal with state 1. So, what has buckling to do with stability? The bigger question is state 2 in stable or unstable equilibrium? Usually, state 2 after buckling is either neutral or unstable equilibrium. Thus, there are two topics we will be interested in this course. Buckling, sudden change in deformation from state 1 to state 2. The next one is stability of equilibrium. As the loads acting on the structure are increased, when does the equilibrium state become unstable? The next one is the equilibrium state becomes unstable due to 1. Large deformations of the structure. Number 2. Inelasticity of the structural materials. Buckling takeaway. The phenomenon is defined as a sudden change of deformation from the normal natural mode to the somewhat unexpected unnatural preferred alternative mode. The collapse mechanism is uncontrolled deformation followed by yielding. Failure occurs as a result of combination of yielding and instability, not formation of plastic hinges. The cause is only compression. The nature of deformation can be flexural or torsional. Hence, buckling failure can occur at a lower load, much lower than that of strength of the material. As the definition suggests, the failure is often sudden and without prior sign of distress. Now, let's look at the types of buckling. The buckling can be classified based on several definitions. One is based on the load deformation relationship. So, in load deformation relationship, we can have bifurcation buckling, we can have limit point buckling, we can have finite disturbance buckling, we can have snap through buckling. And based on modes of failure, we can have local buckling of plate, we can have flexural buckling, basically doubly symmetric columns. We can have torsional buckling, which is specifically exhibited by cruciform cross sections. The fourth one is flexural torsional buckling, typically occurs in singly symmetric columns. The fifth one is the lateral torsional buckling, it occurs in a beam. The sixth one is the distortional buckling, basically beam with slender webs exhibit distortional buckling. And seventh one is the buckling of the entire frame. So now let's look at one by one. What is bifurcation buckling? So when the deformation that occurs in one direction suddenly changes to another direction, it is referred as bifurcation buckling. When a concentric compressive load is applied on a perfectly straight column, the column shortens or experiences axial deformation in the direction of the applied force. This picture on the right side gives you a perfect column when the applied load is less than the critical load. Then you can see that when the applied load is equal to the critical load, there is a small axial deformation which is measured as delta at the bottom of the picture. When the applied load gradually increases, there comes a point when the mode of deformation suddenly switches from one of axial to one of lateral, in which the column buckles in a direction perpendicular to the direction of the applied force. The load at which this occurs is referred to as bifurcation or critical load. As you can see from the right side of the picture, when P is greater than P critical, in addition to axial displacement, you can also see a sudden lateral displacement measured by small delta. This slide shows you the load displacement relationship when the applied load is reaching P critical. The point at which the applied load reaches P critical, it is called bifurcation point. Deformation or the buckling that corresponds to this one is called bifurcation buckling. So the examples are perfectly straight column subjected to an concentric compressive load, geometrically perfect thin plate subjected to an in-plane compressive force, and guide tower. The next one is the limit point buckling. The limit point buckling is basically given as when a single deformation mode exists throughout the loading history, it is referred to as limit point buckling. The deformation increases when the load increases from start of loading to failure. The maximum load that the structure can carry before failure is referred to as limit or ultimate load. As you can see from the picture, there is an initial deformation here, delta naught, which is called initial imperfections along the length of the column. And when the applied load reaches P critical, then there is another delta, which is basically on top of the imperfection. And when we plot the load deformation plot, we can see that it starts from delta naught, which is the initial imperfections, and it reaches the ultimate, which is called P critical, also known as limit load. So the examples of such kind of limit load buckling is geometrically imperfect, or it is also called as crooked columns subjected to concentric compressive forces. Finite disturbance buckling. The finite disturbance instability occurs when a compressive force is applied along the longitudinal or axial direction of a thin-walled cylindrical shell. The load deflection curve rises to the theoretical load critical, N critical, which you can see from the right side, then drops suddenly to a lower value for the structure to maintain equilibrium. So the slightest imperfections drastically reduce N critical. The fourth one is given as snap-through buckling. So snap-through buckling, also known as oil can buckling. The snap-through buckling is characterized by a sudden increase in deformation under a constant load. You can see on the right side a picture of a shallow arch, which is subjected to a radial compressive load. So for some systems, such as in-plane buckling of a shallow truss or arch subjected to a transverse load, and buckling of a shallow spherical cap subject to radial load, once a load reaches a certain value as denoted by point A, the system can maintain equilibrium only if the displacement snaps suddenly from point A to point B as shown by the solid horizontal line. The dotted curve line represents an unstable equilibrium state and can be observed only if the system is subjected to an ideal displacement controlled condition. With this one, we will wind up the class today and we will continue the conversation on buckling in the next class. Thank you very much.